all the aspects of relative motion and kinematics with that is completed in the last lecture. Today we are in a position to start the next topic in physics, which will be circular motion. We will keep some time aside for doubts and questions if required, okay, from kinematics. But otherwise, we are done with the chapter. Yes, circular motion finally. So let's begin. So the definition of circular motion is very simple. It's defined in the same way that in coordinate geometry or mathematics, a circle is defined. It has to do with the fact that on the circle, the distance at every point from the center is a fixed quantity, which we call the radius. So circular motion is basically motion of an object or a particle or whatever, which is along such type of a circular path that at every point on its path, its distance with respect to the fixed point, the so-called center of the circular motion, which will remain constant. So we can define circular motion in this way. It is first of all a motion in a plane. It's a two-dimensional motion. So it is motion in a plane of two-dimensional surface such that the distance from a particular fixed point or the center of the circle remains constant. So the path or trajectory for such a motion is called a circle. It can be represented by the equation of a circle, which you are familiar with. Yes, and that distance is called the radius. Okay. Fixed distance from the center is called the radius of the circle. Okay, so if we convert this wording based definition into a mathematical definition, we can say that let us define the two-dimensional plane in which the motion is happening as the xy plane, and let's define the center as the origin. So this definition now implies that if the motion is in the xy plane with the origin at the center, or rather the center at the origin, center of the circular motion at the origin, then at any position so if the origin is becoming the center of our circular motion, then at any point of time, if a particle is located at a point like this, whose coordinates are x, y, and therefore its position vector with respect to our origin is xi cap plus yj cap, then the magnitude of this position vector should be constant. So square root of x square plus y square, which is the magnitude of r vector, should be constant, or we can say that x square plus y square is equal to r square. So this equation now represents the trajectory of the circular motion. So this is a circular path or trajectory with center as the origin and radius equal to r. And as you know, this, when we plot it, it's represented by a shape which looks like this, round shape, which satisfies this condition that every point on it is equidistant from the origin. Yeah, that is the definition of circular motion. That Anshul, that is the definition of circular motion, that the distance from a fixed point should remain constant. So if we are defining that fixed point from which the distance should remain constant, that point is called the center. So if we take the center at the origin of our coordinate system, okay, that means the position vector of the particle at any point of time during its path or during its motion, at any point on the path, the position vector should be such that its magnitude remains constant, because basically the distance OP should remain constant, which is called the radius. So mod of r vector is nothing but the radius of the circle. Hope it is clear now. Okay. Okay, now next thing you see is to describe the circular motion, we define something called angular parameters. Just like we had started kinematics by defining some parameters or variables. So the description of circular motion in physics also starts with the definition of certain types of parameters. And these have to do with angles. So they are called angular parameters. So again, geometrically, if this is a representation of our circular path, and this is our chosen system of axes, where of course we have selected our axis such that the motion is happening in the xy plane. So the circle lies in the xy plane, and the center of the circle is the origin of our coordinate system. Then at any instant of time, if the position vector of a particle is like this, so this is the position at some time t. So R is what we call the instantaneous position of the particle P in circular motion as seen at the instant of time t equal to t. So this R will be equal to some x I cap plus y j cap. Now if the angle made by this R with respect to the x-axis is theta, then you can see in the diagram that this is x and this is y. So this says that x is equal to r cos theta, y is equal to r sin theta, where the magnitude of r is constant, is the radius, but theta is instantaneous. That means it is changing with respect to time. It's a variable because the particle might be moving in this kind of path. So after some time, at some different time, the particle will now be located over here. Let's say at t equal to t plus delta t, the particle is now located here. So its position vector has changed in such a way that the angle has changed, but the magnitude is remaining constant. So now from here to here, the extra angle it is reaching, that will be called delta theta. Okay, so now we define the first angular parameter in our system called angular position. Just like in kinematics, we started by describing position. So in a 1D system, the position was a single coordinate. In a general system, the position was given by a vector. So like that, now in a circular system, the position is given by an angle. So it is called angular position theta. So angular position theta, it is defined as the angle made by the position vector r with respect to the x-axis. Okay, so this is the instantaneous position. And where we use the sign convention that anti-clockwise is positive and clockwise is negative. For example, we say that the angular position is plus pi by 3. It means that on the circle, the position of the particle should be at such a point where it's like this. This is where the particle should be located, so that this angle is pi by 3. But on the other hand, if we say some other particle or at some other time, the angular position is, let's say, minus pi by 6. So that means it will be here. It will be making a clockwise angle of pi by 6 with respect to the x-axis. So that is a sign convention. So this position P prime now is at angular position theta equal to minus pi by 6. Whereas this one here is at angular position theta equal to pi by 3 x in this particular example. Okay. So in general, this is how we define angular position. So one more thing here is angular position theta is expressed in radians. That is a SI unit. And of course, it is a dimensionless quantity. Because angle is dimensionless. Okay. So just note down this first definition, angular position. So just like in straight line motion, for example, we define position as a coordinate. So in angular motion or circular motion, we define the position by an angle. And that is called angular position. Yeah, so angular position, just to answer your question, Shayan, is always with respect to the positive x-axis. Okay, so when we say with respect to the x-axis, we mean with respect to the positive x-axis with the sign convention that anti-clockwise is positive and clockwise is negative. Now, next thing, obviously after position, we define the next thing as displacement. So here we define angular displacement. So just like in regular kinematics, displacement is defined as change in position. So here angular displacement is defined as change in angular position. So it is final value of theta minus initial value of theta. So angular displacement, it equals to the change in angular position. So again, visually, you can understand it this way, that if on a circular path or for a body in circular motion, if let's say at some time t1, at some time t1, let's say the position of the particle was here. So this is r1 vector at time t equal to t1. So this angular position is theta1. Now after some time, suppose the particle has moved along the circle and reached this position. So it's gone on this kind of path and it's reached this position at some time t2, which is t1 plus delta t. So the angular position has become theta 2. So during this time, the change in angular position, which is the angular displacement, will be theta 2 minus theta 1. So this quantity here, this becomes our angular displacement delta theta. So from t equal to t1 to t equal to t2, the angular displacement you can see is theta 2 minus theta 1 in this particular example. So again, this follows the same sign convention. Delta theta being positive means it's an anti-clockwise displacement. Delta theta being negative means it's a clockwise displacement. Okay. And again, delta theta is dimensionless and expressed in radians. That is the SI unit. Okay. So that's about angular displacement. So let's do a quick example to understand this. Calculate the angular displacement of the minute hand of a clock from 12:10 p.m. to 8:45 p.m. What is the angular displacement? You can express the answer in degrees also, but generally it's preferable to use the SI system, so that's in radians. Right. So we had just about started with the explanation of angular position and angular displacement thereafter that. So let's understand this question. So the angular displacement of the minute hands from 8:10 p.m. to 8:45 p.m. has anybody calculated that? Have you got the answer? If you send me the message before, just send it once more because I have lost all the messages. Yeah, so Ishan, you are giving the answer in degrees. All of you are giving the answer in degrees, right? Okay. Yes, you can convert it like that to radians also. So anyhow, let's quickly understand how much that will be. So if we just sort of make a diagram for a circle which is representing the clock, okay, let's say, yeah, in degrees. Okay. So this would be like our for our minutes hand, this would be 0 or 60, whatever. So this is 15, 30, 45. Right. So now like this. So this is where the minutes hand is at 12:10 p.m. So you can see that this angular position, you can write it as, let's say, theta1. With respect to this, the angular position is how much now? 1/3 of this, so 5/6 or 30 degrees. Okay. Whereas at 12:45, that would have gone here. Now remember, we are talking about displacement, so we are only interested in change in position. We are not interested in the fact that it is at 8:45, it has actually gone round the entire clock compared to 12:10. It has gone around the entire clock 8 times and then a further 45 minutes like that. We're not interested in that. We are only interested in the change in position. So at 8:45 p.m., minutes hand is here. So this theta2 I would write as clockwise. So I'd write it as minus of pi or minus 180 degrees. So the angular displacement delta theta, you can see that that will become minus 7 pi by 6 or minus 210 degrees. So basically we can say that delta theta is 210 degrees or 7 pi by 6 in the clockwise direction. The negative sign is just showing you that it is clockwise. Okay. So pretty easy stuff. Okay, so far. Just to explain to you the concept of angular displacement. Okay, now next thing in our set of definitions, let's check how many people. Okay. So in our next in our list of definitions of angular parameters, our next parameter, as you might have guessed, will be from displacement we move on to velocity. So angular velocity now. So this in circular motion or in mechanics for that matter, it is denoted by the Greek symbol omega. Looks like a W, but we call the symbol omega. Okay. So angular velocity is defined as the rate of change of angular position, okay, or you can say displacement with respect to time. So instantaneous angular velocity will be defined as d theta by dt. We can also define average angular velocity as delta theta by delta t. But usually we are more interested in this. So when we talk about angular velocity, we mean instantaneous velocity only, which is instantaneous rate of change. So angular velocity is expressed in radians per second, that is SI unit, and it has a dimension of time inverse. So for example, the seconds hand of a clock has an angular velocity equal to minus 2 pi radians in 60 seconds. Minus because it's clockwise, or you can say clockwise. And the final term, angular acceleration. So again, we use a special symbol alpha for angular acceleration. So angular acceleration is defined as the rate of change of angular velocity with respect to time. So there is also average angular velocity, but very rarely use that term. The more important thing is the instantaneous angular acceleration, which is instantaneous rate of change of angular velocity with respect to time. Okay, so angular acceleration is expressed in radians per second square. That is the SI unit. And the dimension of alpha is t to the power minus 2. Also, it can be defined as second derivative of angular position with respect to time, or also by using chain rule can be defined as omega d omega by d theta. There are these two alternate definitions for it. You just make a note of this, people will continue.
Sir, can you scroll up?
Yeah. Yeah, you wanted me to scroll up to
Sir, can you show that angular velocity? Yes, sir.
yeah, this section.
Yes, sir.
Okay.
Sir, you can scroll down.
Okay, so this is done now. Okay, now see these relationships that we have written over here, they are very similar to like we used to write in 1D motion. If you do a comparison of 1D motion with now circular motion, so we had position, we had displacement as change in position, we had velocity as rate of change of position, acceleration as rate of change of velocity, or second derivative of position, or we could also define it as v dv by dx. Okay, so like that, we have angular position, angular displacement, angular velocity, angular acceleration, which can also be defined as second derivative of position, or it can also be defined in the same way as omega d omega by d theta. So likewise, we also have a situation where for a circular motion with uniform angular acceleration, uniform angular acceleration alpha. That means alpha is constant. We'll have angular velocity at any time is the initial angular velocity plus alpha t, where omega naught is initial angular velocity. We'll have angular displacement is omega naught t plus half alpha t square. And we'll have omega at any time is such that omega square is omega naught square plus 2 alpha delta theta. So again, these equations, they are derived in the same way like we're done for 1D motion with uniform acceleration. It's in there. We had so here alpha is constant. So this equation becomes analogous to this equation. Similarly, now in this equation, the linear parameters are replaced with the angular parameters. Same with this equation. Okay, so once now we are clear with these angular parameters. Next, very important first to understand is the concept of two special unit vectors that are used in circular motion. In circular motion, namely something called radial unit vector, which we denote with the symbol r cap, or sometimes we also use the symbol er cap, and the tangential unit vector, which we generally denote with the symbol theta cap, or sometimes we also use the symbol et cap. So let's understand how these two unit vectors are defined. So if this is the circular path for a given particle, and as usual we have defined our reference axis as the x and y axis like this, then at any particular instant of time, if the instantaneous position of a particle at some time t is over here, this is the position of the particle at some particular time t, so its angular position you can see is theta. Then at that instant we define the two special unit vectors, the radial unit vector and the tangential unit vector, as these two. Wherever that particle is located, a unit vector that is along the direction of the radius or pointing directly away from the center of the circular path, that is called the radial unit vector. And another unit vector which can be drawn perpendicular to its radial one or along the tangent, that is called the tangential unit vector. So this tangential unit vector directly points along the tangent. It is perpendicular to the radial unit vector. So these two are the radial and tangential unit vector respectively. Unit vector, means that its magnitude is 1, but the direction is radially outwards. Yeah. So we use the symbol either r cap or e with a small r subscript cap. So this is a unit vector. Okay, that is a vector of magnitude 1 or unity. Okay, along OP, or what we call radially outwards from the center. And similarly, this is a unit vector along the tangent to OP. That is the tangential unit vector. So obviously, theta cap and r cap are mutually perpendicular. So now you can separately also understand that with respect to our XY system, at any instant of time, wherever the angular position of the particle is, the radial unit vector is going to be along that same radial line. So it's going to be at theta with respect to the x-axis, whereas the tangential unit vector will be at 90 degrees to that one. So this is our r cap and This is a theta cap. Okay. So r cap and theta cap in terms of angular position theta. How do we describe that? So you can see r cap is cos theta I cap plus sin theta j cap, and theta cap is cos of 90 degrees plus theta or pi by 2 plus theta I cap plus sin of 90 degrees plus theta j cap. So this is minus sin theta I cap plus cos theta j cap. So these two expressions now represent respectively the radial and tangential unit vectors in terms of the angular position, the instantaneous angular position. So you can see that as the particle is going round in the circular motion, suppose it's going like this in the anti-clockwise sense. So from instant to instant, your theta is changing. So accordingly, your radial and tangential unit vector is changing. Okay, as you're plugging in different values of theta in these formulae, you can see r cap and theta cap are instantaneous quantities. They're changing with time, but they always remain mutually perpendicular, and their magnitudes are always equal to 1. You can see that at any instant of time, r cap dot theta cap is 1 because they are perpendicular. So very soon we will understand the importance of these unit vectors in circular motion, because whatever vector resolution we are doing in circular motion, like if we are applying Newton's laws and resolving forces, etc., usually the resolution is done according to these two unit vectors. Instead of x and y or I cap and j cap, the resolution is done in terms of radial and tangential, or in terms of r cap and theta cap. So earlier you might have heard of terms like centripetal acceleration, tangential acceleration, centripetal force, etc. So all those terms become easy to define and easy to understand in terms of these unit vectors. So that is why these are extremely important to understand. Okay, now let's look at a couple of things related to these unit vectors before we wind up today's lecture. So now if you look at the position vector r at any instant, you can see that the position vector is r cos theta I cap plus r sin theta j cap, okay, where the radius is constant. This is the constant radius of the circular motion. So we can say that the position vector is that constant radius multiplied by the radial unit vector, where we are making use of this formula. And now based on this, if we look at velocity, the instantaneous velocity vector, not angular velocity, but now we're talking about linear velocity vector. So velocity is defined as rate of change of position or displacement. So that becomes rate of change of this quantity, r cos theta I cap plus r sin theta j cap. So this becomes r into rate of change of cos theta into I cap plus r into rate of change of sin theta into j cap. Okay. Now we'll use the chain rule concept, that rate of change of cos theta with respect to time is derivative of cos theta, okay, into d theta by dt. This is our chain rule. Dy by dx is equal to dy by dz into dz by dx. So that like that. D by dt of this quantity is same as d by d theta of that quantity into d theta by dt. So derivative of cos theta is minus sin theta, and d theta by dt is defined as omega. So it becomes minus omega sin theta. And likewise, the rate of change of sin theta will become derivative of sin theta into d theta by dt. So that is cos theta into omega. So omega cos theta. So now we will plug in both these terms. We plug in them over here. So you can see this will become r into omega with a minus sin sin theta minus omega sin theta I cap plus omega cos theta j cap. So if you take omega common, now you understand the importance of these unit vectors, because you see what you are left with inside that bracket is the tangential unit vector. Okay. Minus sin theta I cap plus cos theta j cap is nothing but the tangential unit vector, which you can see here. This unit vector, that's the same thing as the one over here. So you can see that the velocity's direction is tangential. So you can say that velocity vector is r omega theta cap. So this gives us a very important understanding that the magnitude of velocity is r omega. Very important relation. Okay, the magnitude of velocity is radius into angular speed. Okay, and the direction of the velocity vector is tangential. That is along the tangential unit vector theta cap. So it is perpendicular to the radius along the tangent.
Sir,
Yes,
sir, here velocity and angular velocity are different, right?
yes, they are different things. So this velocity is expressed in meters per second. Angular velocity is expressed in radians per second. So that is why you have the relationship between their magnitudes, that v is equal to r omega. So when you multiply something in radians per second with the radius in meters, you get the unit of meters per second.
So, sir, it is velocity of the particle moving around that
Yes,
circular path.
yes, it is the instantaneous velocity, whereas d theta by dt or omega is the instantaneous angular velocity.
Yes, sir.
Okay, so these become some of the important relationships. Okay, now while we'll conclude today's lecture here, but next time we will take this discussion further to understand acceleration. And we'll get acceleration by differentiating the velocity. And we'll see that when we differentiate velocity, we'll get two components of acceleration. One will be a radial component, the other will be a tangential component. So both the unit vectors r cap and theta cap will come into play when we discuss about acceleration. But so far what we have understood from that, we can understand this visually like this, that if this is the circular motion, and if this is the circular path, so if at any instant the particle is located at some kind of angular position like this, then multiply the radial unit vector with the r cap and we get the position vector r, and draw the tangent to it at that instant. So the velocity vector, instantaneous velocity vector of the particle is lying along that tangent. So the circular motion is happening in this sense. Okay. Then at that very instant, its velocity vector is along the tangent. So if there was suddenly we remove the force acting on the particle and allowed it to continue with its state of inertia, then it would continue along the tangential direction. Its momentum would be along the tangential direction. The velocity is like this. Okay. At a later point of time, let's say the particle has come here. So accordingly, the position vector is now this. Let's say the position vector has now become r prime. So at this point of time, you will see the velocity vector has likewise become perpendicular to r at this point. So it's become like this. So always there is this relationship between velocity and position, that velocity is perpendicular to position vector at any instant. Okay. So another way to understand this is that the approach or separation velocity of the particle towards the center, that should be how much? It should be 0, because the distance is never changing. So there is no approach velocity at any point of time. It's always perpendicular and the center is a fixed point. So the particle is moving in such a way that it at any instant it is neither approaching nor separating from the center. So its distance is remaining constant. Okay, so hope these concepts are clear. So with this, we conclude today's session. Okay. Make sure you revise these definitions and these basic derivations before the next lecture, because we will take the discussion forward with acceleration from here, and we will get into problem solving in the next lecture. So these basics need to be very well understood by them. Okay. So do a revision of this and also continue with your module questions of relative motion and in general of kinematics. Look to complete the exercises of kinematics part 2 in module 1. So that's it for today's session. Yeah, Ishan, I'm keeping the notes for some time. We can note down. Okay. So anyhow, that's the end of today's session. Wish you all the best. Have a nice day.
Thank you, sir. Bye, sir.
Bye.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Hello, sir. Bye, sir.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Bye.
Okay, people. Bye.